Chapter 4. In this chapter, we are going to apply second law to the phase transition of pure substances and study the relationship between temperature and pressure when a phase transition occurs. Let's first go over a few equations we learned in the last chapter that will be used for this chapter. Gibbs energy is the standard state Gibbs energy plus nRT ln P over P naught. P naught is the standard state pressure, which is 1 bar. This equation comes from the fundamental equation dg equals negative SDT plus VdP. If we include the number of moles change, then we need to add the molar Gibbs energy, which is Gm times number of moles change. Gm, the molar Gibbs energy, is called the chemical potential. So the fundamental equation, you need to add mu times dN. Mu is the chemical potential, which is the standard state chemical potential, plus RT ln P over P naught. Now this equation comes from the first one. If we divide by number of moles, then Gibbs energy becomes molar Gibbs energy, which is chemical potential. If we have a container containing several liquids, the liquid that floats on the top is the one has the lowest density. And the one with high density will go to the bottom. So density determines which one goes up, which one goes down, not the total weight. Similarly, we're going to see that for phase transition, it's not the Gibbs energy itself, but the molar Gibbs energy or chemical potential determines the spontaneity of the phase transition. We are all familiar with water phase transitions. Under 1 atmosphere, water undergo phase transitions at 2 different temperatures. At 0 degree, there's a phase transition between solid and liquid. So ice melt if temperature above 0 degree. Below 0 degree, liquid water freeze into ice. At 0 degree, liquid water and ice can simultaneously exist. Between 0 and 100 degree, liquid water is the most stable phase. At 100 degree, liquid water and gas water or the steam can exist simultaneously. Above 100 degree, only gas phase is the most stable phase. And we're going to see what's the relation between chemical potentials at different temperatures. A phase of a substance is a form of matter that is uniform throughout in chemical composition and physical state. Solid, liquid, gases are the most common phases. Usually, only one phase of a given substance is stable at a given temperature pressure. For example, 1 atmosphere, -5 degree ice is the stable phase. But if temperature goes to 10 Celsius, then liquid water will be the stable phase. At some condition of temperature and pressure, 2 more phases may exist in equilibrium. For example, 0 Celsius, liquid and ice can exist at the same time. They are in equilibrium. 100 degree, steam and liquid water coexist. They are in equilibrium. A slight change in temperature pressure will favor one phase over the other. The conversion of one phase to another is a phase transition. The second law tells us that phase transition occurs when the Gibbs energy decrease. So delta G less than 0. Phase transition, two phases can exist at the same time when delta G equals 0. Suppose we have two phases, alpha and beta. An example is steam and liquid water. And assume temperature is 110, then steam will be the more stable phase. So liquid water will spontaneously vaporize to become the steam, and therefore alpha decrease in the number of moles and the beta increase. And there's a spontaneous change from alpha to beta phase. What happens to the Gibbs energy? For alpha phase, the number of moles decrease, and this will decrease the Gibbs energy for alpha phase. And the alpha phase Gibbs energy is calculated by the molar Gibbs energy, which is chemical potential, times the number of moles change. And here, number of moles decrease, and therefore the Gibbs energy decrease. We had a negative sign to indicate the Gibbs energy of alpha phase decrease in Gibbs energy. Now, similarly, in beta phase, the Gibbs energy change is the chemical potential of beta phase times number of moles change. Here, number of moles increase, so we have a positive sign here to indicate Gibbs energy increase in beta phase. The total Gibbs energy is when you add these two together. Now, second law says if this process is spontaneous, then the total delta G must be less than 0. So how do you ensure this is less than 0? We have negative A, alpha phase chemical potential, positive beta phase chemical potential times dN less than 0. So for this to be true, then the chemical potential of alpha must be greater than beta. So the negative part is more than positive part, and the total Gibbs energy will be less than 0. Okay, so in other words, if you have a spontaneous change from alpha to beta, alpha must have a high chemical potential. So alpha have high chemical potential, so the decrease of Gibbs energy in alpha is more than Gibbs energy increase in the beta phase. And that ensures total Gibbs energy decrease. Okay, and therefore the conclusion is phase transition goes from the phase with high chemical potential to that with lower chemical potential. All right, and this is similar to the situation where water always falls from high elevation to low elevation. Phase transition goes from high chemical potential to low chemical potential. In the last slide, we showed that if there is a spontaneous phase transition, the phase transition always goes from high chemical potential phase to a lower chemical potential phase. What if two phases are in equilibrium? So in this case, alpha, beta in equilibrium. Now, even if you have a change, either from alpha to beta or beta to alpha, for example, let's say alpha to beta. So the Gibbs energy change again for alpha is negative mu alpha dN, for beta is positive mu beta for dN. But the second law says the total Gibbs energy shouldn't change. Delta G has to be 0. So when you add this together, it must be 0. So how do you make this to be 0? In this case, the chemical potential alpha beta has to be the same. So mu alpha must equal to mu beta. In this case, then even if you have a change from alpha to beta, delta G will be 0. On the other hand, if beta to alpha, you will see the delta G is still 0 because they have the same chemical potential, and this ensures the Gibbs energy will not change whether you have a small change phase from alpha beta or beta to alpha. They are in equilibrium. Okay, there's no natural direction of the change. By applying the second law to the phase transition, we established the criterion for the phase transition, and that is when two phases or more than two phases are in equilibrium, their chemical potentials must be the same. So for example, we know at 100-degree liquid water and the steam are in equilibrium, and this tells us that the chemical potential of liquid equals the chemical potential of the steam, which is the gas phase, at 100 degree, 1 atmosphere. If two phases are not in equilibrium, the phase transition will occur from high chemical potential to low chemical potential. Okay, and therefore, if you have two phases, liquid water and steam, at 70 degree, and we know steam will automatically condense into liquid, and this criterion tells us that the chemical potential of steam or the gas must be greater than the chemical potential of the liquid water, so that there's a spontaneous change from gas phase to the liquid phase. Now this also leads to an important conclusion, that if you have two phases not in equilibrium, the phase with low chemical potential is the more stable phase, because the phase with high chemical potential will spontaneously change to the low chemical potential phase, and that will be the most stable phase. We now can tell how chemical potential change for water at different temperatures. At 0 degree, for example, liquid and the ice are in equilibrium, so the chemical potential of liquid equals the chemical potential of solid. Below 0 degree, ice is the most stable phase, and therefore the chemical potential of ice is the lowest. Okay, so if you have liquid chemical potential must be greater than the chemical potential of solid, so liquid will spontaneously freeze. Between 0 degree to 100 degree, liquid water is the most stable phase. Okay, so if you have gas phase, it will condense. If you have ice, it will melt, and therefore the chemical potential of the liquid is the lowest, is lower than gas phase, lower than the solid phase. At 100 degree, liquid water and steam are in equilibrium, so they have the same chemical potential. Above 100 degree, steam becomes the most stable phase, and so steam has a chemical potential lower than liquid or solid. So far, we have shown that it's the chemical potential that determines the spontaneity of phase transition. And so let's go over the equations that we are going to use in this chapter. The Gibbs energy change is contributed by temperature change, pressure change, number of moles change. The molar Gibbs energy represents the change of Gibbs energy due to the number of moles change. And so if temperature pressure is constant, the Gibbs energy change is the chemical potential times number of moles, and the total Gibbs energy is the chemical potential times total number of moles. Chemical potential is molar Gibbs energy. Because molar Gibbs energy is the standard state molar Gibbs energy plus RT LMP over 1 bar, so chemical potential is therefore standard state molar Gibbs energy plus RT LMP over 1 bar. And these are the important equations that we are going to see again in the later chapters or later of this chapter. Here shows a typical phase diagram for pure substance. This phase diagram shows the regions where various phases are thermodynamically stable. At high pressure, low temperature, solid phase is the stable phase. At high temperature, low pressure, vapor phase is the stable phase. In between is the liquid. The phase boundary phase diagram also contains three phase boundaries: the solid-liquid phase boundary, the liquid vapor solid phase boundary, and the liquid vapor phase boundary. Any point along this phase boundary means two phases can exist at the same time. They are both thermodynamically stable. For example, a point here, all right, so let's say this is point 1. Okay, so on point 1, liquid and vapor can both exist simultaneously. So thermodynamically, we know at this point, chemical potential of liquid equals chemical potential of vapor phase. And any point inside a region such as number 2 means solid is the most stable phase, so the chemical potential of the solid should be lower than liquid or gas phase. It's the lowest. Now along this phase boundary, for example, point 1, number 1, you have two phases exist simultaneously, and therefore the temperature should be the boiling point. Okay, because at this temperature, the two phases can exist at the same time. But we know that for water, we usually say the boiling point is 100 degrees. But why here you can have many points? That means you have many boiling points. So why is that? Well, the reason is that when we say the boiling point is 100 degrees for water, we assume pressure is 1 atmosphere. In fact, when you change temperature, when you change pressure, the boiling point also changes. And so this is the curve that will tell you the boiling point and the pressure relationship. So that's one thing we are going to derive later in this chapter. Okay, and we also see in the phase boundary there is a triple point. Okay, triple point is a special point in the phase boundary. On this point, three phases can exist simultaneously: solid, liquid, and the gas phase. They are all stable at this point. So the chemical potentials are all the same. All right, triple point is unique to a substance. For example, for water, the triple point is 273.16, 611 Pascal. You cannot change triple point. You can change melting point. You can change boiling point. Okay, if you change pressure, boiling point change, but you cannot change triple point. All right, it's determined by nature. Phase diagrams can become very complicated, even for water. So for water, you have a triple point, you have ice, you have vapor phase, and the liquid phase. Now, at a very high pressure, ice can change phase too. So you have ice 1, ice 2, ice 3, 4, 5. So you have more triple points and boundaries at high pressure for ice. This is the phase diagram for carbon dioxide, which follows the typical pattern for pure substance. The triple point is about 5 atmosphere, and the temperature is 216 Kelvin. And so according to this phase diagram, if we want to make liquid carbon dioxide, one way to do it is to compress gas phase to pressure above 5.11 atmosphere. Another important thing to notice is that all these three phase boundaries, they have a positive slope. A positive slope means when you increase pressure, when you increase temperature, pressure increase. Now, what does this pressure represent? Okay, how do you interpret this phase diagram? Let's take this liquid vapor phase boundary as an example. Okay, so one way to think about this is this pressure is the vapor pressure of this substance. In this case, is carbon dioxide at a different temperature. So here it tells you that when you increase temperature, the vapor pressure increase of carbon dioxide. Now, can you increase vapor pressure indefinitely if you increase temperature? The answer is no. The maximum vapor pressure you can reach is the external pressure. So if you have external pressure 1 atmosphere, the maximum vapor pressure carbon dioxide can get is 1 atmosphere. So what happens is 1 atmosphere, the substance start to boil. Okay, so the liquid boils when the vapor pressure equal external pressure. All right, so another way to look at this phase diagram is that this is external pressure. Instead of vapor pressure, it's the external pressure, and then this temperature will be the boiling point, because this is when the temperature gives you a vapor pressure equal to the external pressure, then it starts to boil. So that's the boiling temperature. This is the liquid vapor phase boundary for water, and you can see here the vapor pressure increase with temperature. At very low temperature, vapor pressure is very low. Now at high temperature, vapor pressure approaches 1 atmosphere. At 100 degree, vapor pressure becomes 760 torr, and that's 1 atmosphere equals external pressure, and that's when liquid water start to boil. Okay, so is that possible? You can make water boil at let's say 40 degree. Okay, can you let water boil at 40 degree? Well, the answer is yes, if you make outside or external pressure very low, equal to the vapor pressure. So in this case, it's about let's say 80 torr. So if you use a vacuum pump to pump, the gas phase becomes about 80 torr. Then at 40 degree, the vapor pressure will reach this external pressure and it start to boil. In this slide, we are going to derive an equation to describe the phase boundary in the phase diagram. Okay, this phase boundary can be any of those three. It can be liquid vapor, liquid solid, or vapor solid. All right, now let's start with point A. Okay, the temperature is T1, pressure is P1. So because this is on the boundary, phase boundary, that means the two phases are in equilibrium. So alpha, beta are in equilibrium, so the chemical potential must be the same. Now when the temperature change from T1 to T2, there must be a corresponding pressure change from P1 to P2 so that the two phases are still in equilibrium, because they are still on this point is still on the phase boundary. That means the two phases are still in equilibrium. So the chemical potential at the point B for alpha phase, let's say prime, chemical potential for alpha becomes prime, should equal to the beta phase prime. All right, so before the temperature pressure change and after the temperature pressure change, the chemical potential remains the same for alpha and the beta. That means the change of chemical potential for alpha phase due to this temperature pressure change must equal to the chemical potential change for beta phase due to the temperature pressure change. According to the fundamental equation, the chemical potential change can be calculated by negative entropy times temperature change, volume times pressure change. For alpha phase, we use entropy of the alpha phase. It's the molar entropy of the alpha phase, molar volume of the alpha phase. And for beta phase, the chemical potential change should equal to the negative molar entropy of beta phase times temperature change, molar volume of the beta phase times pressure change. Because these two chemical potential change are the same, so we have this equation. The left side represents the chemical potential change for alpha phase, and the right side is the chemical potential change for the beta phase. So now let's rearrange this equation. So we can move this term to the left side, so negative becomes positive. So we have entropy of the beta phase minus entropy of the alpha phase, all right, times dt. Okay, and now let's move the pressure change from left to right side, so that will change the sign of the alpha to negative. So volume of the beta phase molar volume minus alpha phase molar volume times pressure change. Okay, so these two are the same. Okay, now we can simplify this. Now the entropy of the beta minus alpha, this means the entropy change between the two phases. So this is actually the phase transition entropy change. Okay, entropy change from alpha to beta. So that's the phase transition entropy change times temperature change. And the volume of the beta minus alpha, that will be the phase transition volume change, because that's the volume of the final phase transition phase beta minus initial phase alpha. So that's the change of volume due to the phase transition times dp. Okay, so if these two are the same, then we can again rearrange. We have this equation. So dp divided by dt should equals to delta S, okay, entropy, phase transition, divided by volume change due to the phase transition. This equation is called the Clapeyron equation. So what does the Clapeyron equation tell us? The left side is dp divided by dt on the curve, all right? That's the change of pressure, okay, the pressure change. So this pressure change divided by volume change, or the temperature change, and that's the slope. Okay, this tells us the slope of this phase boundary equals to the entropy change, phase transition entropy from alpha to beta, divided by the phase transition volume change from alpha to beta. We have shown that a typical phase diagram contains 3 phase boundaries. All of them has positive slope. Now we can use this Clapeyron equation to justify this. Okay, so let's look at one example from liquid to vapor phase, phase change. So liquid goes to vapor phase. The entropy change from low to high because liquid has less freedom, and gas phase, vapor phase, has high freedom, more freedom, and therefore entropy increase, delta S must be greater than 0. Now, from liquid to vapor phase, the volume expands, and therefore delta V also positive. And therefore, according to Clapeyron equation, the slope dp dt over dt should be delta S over delta T, delta V, which is positive. All right, so slope is positive, and therefore vapor pressure should increase. Okay, the slope is positive, so vapor pressure increase with temperature. Similarly, if we look at solid to gas phase, the molar volume must increase, expand, okay? And gas phase has more freedom, so delta S is also positive. So again, the slope is positive, all right? Now, what about the solid to liquid? From solid to liquid, the entropy also increase. Okay, liquid has more freedom, solid has less freedom, so delta S is greater than 0. But what about volume change? Most substance, when they melt, volume increase. Now, one exception is water. Okay, when water melt, ice melt, the volume actually slightly decrease, and that's why ice float on top of liquid. Okay, and therefore, if you look back at the phase diagram of water, you will see the slope slightly decrease. All right, slope is negative. The Clapeyron equation tells us that the slope of the phase boundaries can be calculated by the phase transition entropy divided by the phase transition volume. Now, the last chapter, we learned that phase transition entropy can be calculated by the phase transition enthalpy divided by temperature. So, if we replace the phase transition entropy by enthalpy divided by temperature, we have the equation to calculate the slope, which is the phase transition enthalpy divided by temperature over phase transition volume. And this equation is also called Clapeyron equation. The Clapeyron equation we derived from last few slides applies to all phase boundaries. So in these slides, we are going to focus on the phase boundary between liquid and the vapor phase. So this involves phase transition between liquid and the vapor phase. In this Clapeyron equation, delta V is the volume of the gas minus volume of the liquid. Now, because volume of liquid is much smaller than the gas phase, therefore this delta V is approximate to be the volume of the gas, and liquid volume can be negligible. All right. Now, if pressure obeys ideal gas law, then volume obeys PV equals nRT, so it will be nRT divided by P. All right. Now, if it's one more, then it's just N, so RT times P. Okay. So we replace this by RT divided by P, and the P can go up here times P. All right. So P times delta H divided by RT squared. So here becomes RT squared because you have a temperature here. All right, now we can divide by pressure on both sides. So that gives you this equation. 1 over P dP equals delta H over RT squared times dt. Our goal is to find the equation between pressure and the temperature. We need to integrate these differentials. Okay, so to integrate, we integrate both sides, right? Now the left side, you have seen this many times. 1 over x dx is ln x. So the left side is ln P2 over P1. The right side, because if we assume enthalpy doesn't change with temperature, and so the integration becomes delta H over R integration T squared dt. The integration 1 over T squared is negative 1 over T. Okay, so the right side becomes negative delta H over R 1 over T2 minus 1 over T1. And this equation is called Class's Clapeyron equation. So this equation tells us that if you have 2 points on this liquid vapor phase boundary, for example, point 1 has T1, P1, point 2 has T2, P2, then this pressure temperature are related by this equation. So if we know one point, all right, we can calculate another point. We can calculate vapor pressure at different temperature, or we can calculate what is the boiling point at a certain external pressure. Okay, so we'll see this example in the next slide. Sample question. Estimate the boiling temperature of water at top of Pikes Peak in Colorado, where the pressure is 0.85 atmosphere. So we know the water boils at 100 degrees when pressure is 1 atmosphere. But when you increase elevation, in this case, the pressure becomes only 0.85. The question is, what is the boiling point? Classical Clapeyron tells us that boiling point and the pressure are related by this equation. So in this equation, T1 is 100 degrees, you need to change to Kelvin, and the P1 is 1 atmosphere. All right. Now we know one point on the phase boundary. The second point on the top of mountain, we know pressure, okay, which is 0.85. We want to calculate T2. So plug in all the data. Delta H is 40.6 kilojoule. So you need to change to joule. All right. So times 1,000, and R is in joule. So here, plug in everything. All right. The calculated temperature is 368 Kelvin, which is 95 Celsius. So this tells us that when you increase elevation, the pressure decrease. When pressure decrease, boiling point decrease. Here, the boiling point is about 95 degrees. So imagine you cook food, and that will take longer time because water boils already at 95 degrees. So it takes longer time for the food to be well cooked. Okay. On the opposite side, the high pressure cooker exert a higher pressure than 1 atmosphere, and that will lead to a higher boiling point. So the boiling point inside the high pressure cooker is more than 100 degrees, so the food cooks faster. We derived the classical Clapeyron equation, which applies to liquid vapor phase boundary. We started with this Clapeyron equation, and we assume the delta V is approximately the volume of the gas, because volume of the liquid is too small. All right. We also assume delta H is constant. So two assumptions. Okay, this is constant. So the question is, are these assumptions also valid when we talk about the solid vapor phase? If so, then the classical Clapeyron equation also apply to this phase boundary. The answer is yes, because from solid to vapor phase, the volume change can be approximated by volume of the gas, because the solid volume is very small compared to the gas phase, and the delta H can be considered a constant, and therefore this equation also apply to the solid vapor phase boundary. The only difference is the vaporization enthalpy is replaced by the sublimation enthalpy from solid to the vapor phase. We have derived the classical Clapeyron equation, which applies to both liquid vapor phase boundary, solid vapor phase boundary. And the reason is, when we derive the equation, we can make the same assumption. The assumption, however, cannot be applied when we look at the solid liquid phase boundary, because the volume change cannot be approximated by the volume of the gas. Neither solid nor liquid is a gas phase, so it has nothing to do with the gas phase. And apparently, we cannot use the same approximation, same assumption, and therefore the final equation cannot be applied. We have to derive a separate equation for solid-liquid phase boundary. Okay, and in this case, for this phase boundary, the enthalpy change is called the fusion enthalpy. The volume change is called the fusion volume change. Now, even though the volume change cannot be approximated by the volume of the gas, we notice that this is a constant. Okay, the reason is both solid and liquid they have constant volume that do not change when you change temperature, pressure. So delta V is constant, delta H is also constant, and this makes integration much simpler. Okay, to integrate, first we need to separate variables because you see both sides has temperature. So to do that, we times dt to cancel temperature on the left side. All right, so the equation now becomes dP equals delta H over delta V. Remember, this is a constant, times dt over T. All right, so integration on both sides. The left side is just P2 minus P1. On the right side is delta H over delta V, which is a constant, integration T dt. And this integration is ln T2 over T1. All right, so the equation now we have is the pressure, all right, equals initial pressure. So the star means initial pressure. So you can think about this as P1 plus delta H fusion enthalpy over fusion volume ln T over initial temperature. All right, so when the temperature change is a small number, when the temperature is very close to the initial temperature, then natural log T over T initial can be approximated by T minus initial temperature divided by initial temperature. And this equation applies to solid-liquid phase boundary. We have discussed this before. On this phase diagram, the vertical represents the vapor pressure of solid, liquid at different temperature, or we can consider this as external pressure. Then the temperature will be the melting point and the boiling point. And this diagram says that melting point, boiling point are function of external pressure. All right, they change, the varies, okay, when the external pressure changes. However, there's only one triple point. The triple point is unique to a given substance. It never changes. In summary, in Chapter 4, we first established the thermodynamic criterion for phase transition. Phase transitions always go from high chemical potential to low chemical potential. When the two phases are in equilibrium, they must have the same chemical potential. So mu alpha equals mu beta. Based on this equation and the fundamental equation, we derived the Clapeyron equation, and that is the slope of all three phase boundaries, dP over dt, equals delta S over delta V, or delta H over T delta V. For solid vapor phase boundary and liquid vapor phase boundary, both phase boundary involves vapor phase. We can make assumption that the volume change is approximated by the volume of the gas, which obeys ideal gas law, and the enthalpy change is constant. So based on this assumption, we derive this classic Clapeyron equation. So this equation applies to both liquid vapor phase boundary and the liquid solid vapor phase boundary. The only difference is one is vaporization enthalpy, one is sublimation enthalpy. Now for solid liquid phase boundary, then we assume the volume change, delta V, is constant. Delta H is also constant, so we derived this solid liquid boundary equation. Here's a simple question to construct the phase diagram for carbon dioxide. So we look at the three equations we listed in the last slides for solid, liquid, liquid vapor and the solid vapor phase boundary, and we have the sublimation enthalpy, fusion enthalpy, triple point temperature pressure, and we also have the density of solid, density of liquid. These two are used to calculate the volume change for the fusion volume change. So plugging the data into the three equations, okay, we just construct the phase diagram. Here shows the constructed phase diagram.